Hello, everybody, and welcome to today's use case team of ODTN. As usual, we're going to start with the agenda. Please put your name on the list if you have not already done so for today's meeting. And today we're going to discuss many points. First of all, thanks everybody who contributed to the blog post for phase 1.0 demo. I'm waiting on Greg Cross from the ONF, which is our responsible for PR, to publish it. And that would we will be good to go on that side. So thanks everybody for contributing the videos, the script of the blog post, and getting a proper clearance inside your companies. That was very good in my opinion, and I think it's a good milestone to share, and so people can learn about what we did in phase 1.5. So regarding TAPI 2.1, I see Karthik on the call. I don't see Stefan, so I'm gonna defer his presentation again. I don't know if when he's gonna do the presentation it would be still useful and relevant, but we'll see. So I know that, and please Karthik correct me if I'm wrong, I know that you are planning to release TAPI 2.1 tag it at the end of August, which is basically now. So I know that
right. It's a release candidate.
Okay, good.
So it's not a release because release candidate we'll probably have 2 or 3. All it means is like now it's for review. We have frozen the features. We will not be adding new features in, but we'll just now do more bug fixes or issues. I mean, generally. But the release will happen probably by September. We always look for quarter ends. So September end, but the release candidate itself should be good enough. We don't expect major changes to this.
Okay, so that's great information, and so that was basically the state of TAPI 2.1. Anything to add, Karthik or Lyndon?
No. I would expect this group to review it and be the source for any changes between RC1 and RC2.
Okay.
Because I would definitely try to avoid changes based on more standards discussion, but more give priority to anything that's coming out of implementation related issues.
Okay. Yes, I will make sure that we review it, and as soon as the RC candidate is out, I'll share it with the group in a proper email so everybody can review it. Okay, perfect. I'm going to defer Stefan's presentation to next week, and especially I ask everybody to take a look at the new photonic media.yang model. This model here, because this is a completely new model that we're going to use to express the optical parameters both from the northbound and the southbound. So please take a look at that. Okay, so let's come to the meat of today's meeting, if I could say so. Yesterday, and thanks to everybody who participated, we had an implementation discussion of phase 1.5 and 2.0 to come up with the document I'm going to present to everybody today. Most of the people on the call were actually present yesterday, but yesterday was more of a technical discussion on some open points. Today, I want to keep it more of a, okay, this is what we're going to do, and see if there are any comments and clarifications on this. So the document is this one. It's called Phase 1.5 and Phase 2.0 Architecture. Let's start from the northbound. This, and I'll let Karthik speak to it a bit, but this is the current existing solution that we have with ODTN Phase 1.0. The only changes from the northbound point of view will be that we will update TAPI to TAPI 2.1. We need to update TAPI to TAPI 2.1. And augment also the TAPI topology model to TAPI 2.1. But code-wise, it would, at least from the RESTconf perspective and the northbound perspective, it will stay the same as it is right now, except for the few changes, but I suspect that they will be very few for TAPI 2.1 augmentation. Regarding on how to use this code and how to properly issue a request, connectivity request for phase 1.5 and 2.0, yesterday we had a discussion, and we had a discussion previously with some of the folks on the call, and yesterday we discussed it a bit more, if we needed to do one or two connectivity requests, meaning one connectivity request would be an end-to-end between the client-side ports of the transponder, and ONOS would take care of all the rest. Or we will need to do two. One to provision the layer 0, meaning the OLS or the RODMs. So line side of the transponder to line side of the transponder, and then create another one for the layer 2, which would be line side of the transponder to client side of the transponder on both sides. I know Karthik created a very good presentation on what TAPI can do in this realm, and especially if it can express how it can express this requirement that we have. So I'll give Karthik the mic, and he can give us a bit of overview of what TAPI can do and his proposals.
Thanks, Andre.
Do you want me to make the presenter?
Actually, I can grab it because I was doing the TAPI call just before this. Okay.
Aha.
We are using the same license.
Yes, Bills.
Yes. Okay. So can you see my screen?
Yes.
Yeah. So this presentation is actually available on the TAPI contributions page. I can send the link in the chat after this, after I've presented. So you can put in the notes. So you can look at it. So just a note that I've just been able to create one scenario, and the idea is that we'll be creating some more scenarios, and we'll update it like in like a couple of days. So you can view it, and I've tried to animate things so that I can present information in sort of I would say structured way. So it's best viewed if you use it in presentation mode. So you can do that. So right now I have one use case, but some assumptions for this use case. I believe this is the use case that we are talking about in ODTN, but I would want to confirm it today. The use case is like you have the DSR connectivity service, it's the L1 connectivity service or L0. So in MEF, they call it L1 connectivity service, which is the DSR is a TAPI term, digital signal rate. Basically, it could be one of the ODU clients, and or L0 is like basically the photonic layers. Also, like we are in MEF and TAPI, we are working on L1 ODU connectivity, but this is not right now the focus here, right? So, and I'll explain what I mean by DSR versus ODU just in a second. So the assumption here, the edge devices, the transponders are pretty simple in this use case, at least, with no switching capabilities. That's only mapping. So it's not switching Ethernet or it's not switching ODU. So it's just taking whatever the constant bit rate or the ODU clients and mapping into ODU, and actually, and then modulating it and handing off to OLS for switching. This can be easily extended to ODU and Ethernet switch, and there are TAPI contributions available on various ways you can model these switchable devices. Also, not including protection, resilience scenarios or OAM, because it can get pretty messy and complicated. But these are something we can look for future once we go past the simple use case. Also, the photonic arrangement is pretty simple for this use case, assuming that there is single lambda per transponder line port. That is, there is no muxing on the transponder side. And also a single lambda is associated with an user connectivity service or the user DSR. And I'll show it in the figure what I mean. But what it means is there's no multiplexing. It's not a mux ponder in this use case, it's a transponder, right? And this lambda is carried over this a single wide media channel, right? So, and again, in the figures, I can show what I mean later on. And there are more cases which are in TAPI contributions, which is not in this slide deck. But they are more like fragments. They don't describe the whole scenario. They just pick up and they zoom in into a view and describe all this in very fragmented way. So eventually, at least if I find that we are discussing some other use cases, I'll create some slides for those. So the initial use case here, and I presented it from my viewpoint, but this is more like done from the perspective of explaining the concepts. So this scenario may not be the preferred one that we use, but I just use this as a starting point. So the first case is, before I go to the case and describe the title, these slides only deal with TAPI interface views, not internal, right? So I'm only discussing the TAPI, NBI, and what gets exposed on the NBI and the SBIs, not how it's modeled internally in ONOS, which probably Andre will do it later in this discussions. So in here, there is a ONOS client, and I'm assuming that it's managing some L2, L3 switches, something like, I don't know, it could be open flow switches or it could be simply orchestration system, doesn't matter. And there is an NBI context, ONOS NBI, which is TAPI. And there is a ONOS SBI, which is same as the OLS NBI context, right? So the same kind of information, or rather the information that's exposed by the OLS controller, I'm calling it ONOS SBI, or that's what gets it.
Sorry.
Okay, sorry. Okay, I thought there was a question. Okay, right. And so this is how the high level the figure is put in. And the first scenario is the OLS topology is not exposed on the ONOS NBI. So the ONOS NBI context has only the transponder nodes, and in TAPI we allow recursive decomposition of nodes. So you can have a single node on the top, and then the node can have its own topology, right? So I've just shown it. Doesn't have to be done like this, but just for the use case. And in TAPI, what we really expose is the service interface points. So I'm just calling it DSR unis and photonic NNIs. So the DSR service interface points advertises supported capacity and client supported audio clients and etc. Right? So these are the client types that you support, because most vendor devices do support multiple audio client types and capacity. And there may be some more information, but these two are the main. While the photonic SIP advertises the supported spectrum, the central channel, the central frequency, and the modulation format, like the powers and so on, right? What it can support, what you can do on the transponder, right? So this is what is exposed to the NBI. Also, there's one DSR SIP per transponder client port. Now, TAPI allows mapping, more complex mapping, where you can have one SIP that maps to multiple client ports. But let's keep this simple and just assume there is a service interface point per transponder client port. And there is one photonic SIP per transponder line port, right? So are there any questions up to this point?
Just the number of transponder line ports, they are fixed. I guess they are not, you have to define it's a fixed number. They are not variable, right?
They're not variable, and in this scenario, I'm assuming only one. And I'll create a scenario too where I have mux ponder, but I just wanted to go step by step.
Okay. Perfect.
Right. Yeah. And on the photonic side, on the OLS side, there is another photonic SIP exposed, which is there's one SIP, one service interface point per ROADM add drop port. Right. So we're just keeping it simple so that it makes our mapping very easy. Now, if you see, there is a stack of here. The purple nodes are the node edge points. This is the media channel connection endpoint. I have not labeled it. I'll do it before I upload it again, next version. This one, there is some discussion on TAPI, what to label it. There are two options. One is OPS, optical physical section. Other is OMS, optical multiplex section. But irrespective of that, it basically tells you like what is the spectrum available at this port, right? Total spectrum. So that's what it's supposed to be. But just ignoring that, right now, this is the starting point that you would go. And one point here is, in TAPI, we don't specify when you have multiple domains. Now, this is a multi-domain use case, right? So you have a controller for OLS, an OLS controller for ROADM, and a separate controller for transponders, right? So now you have to map the service interface point, which is advertised by this OLS, to the service interface points on the photonic side, on the line side. Now, TAPI does not prescribe how this mapping is done, right? As a standard, we don't do it. We just leave it up to the implementation agreements. So there are a few options. In the previous demos where we did, we either had like config file where we say like sort of lab setup or something saying this port maps to this port, or we use some labels in these SIPs like location info, or sometimes something called plug ID, physical link UID, right? We use some IDs that was advertised by this. So, but it was something that was commonly provisioned beforehand into these devices or in the controllers, and they were exposed. So it allows this controller to map this, I would say, interface points between domains, right? And TAPI does not tell how to do it, but Andrea also mentioned, like he was in the previous TAPI call, that it could also be provided by the user, like through the API, like how to map which SIP maps to which, right? So that's also an option. So this is something that we may have to nail down how we want to do this mapping between OLS, photonic service interface points, and the transponder ports, line ports. Also, the assumption here is the OMS and OTS connectivity is pre-configured. This is just to make the use case simple, so that we don't have to deal with like connectivity between ROADMs and like inline amplifiers and so on. So it will simplify from photonic perspective, but the path calculations. It doesn't make it take all the complexity away, but it does take out some complexity, because if you want to include this, you have to really get down into optical parameters and physics to really set this up. So right now, I'm assuming that for this use case, it's done beforehand. Now, the first thing that ONOS has to do is to retrieve the OLS topology, so it understands the OLS topology. I believe that we were discussing initially a single node view, but now, in my opinion, we have, as a group, trending towards actually exposing the OLS topology. But I've shown both. Either you can display this as a single node, or expose it as a single node, or you can actually expose the actual topology as OMS links, right? You can expose the OTS links too, but assuming that OMS has been provisioned.
And assuming you expose only the single node topology that you were mentioning, and assuming you are only exposing the service interface points of the photonic NNIs, what information is contained in this photonic NNIs in that particular case? If only the photonic NNIs.
The reachability will be like, yeah, the reachability might be right now, then have to be sort of, you have to assume in the simple use case, you can connect any SIP to any SIP then without this topology information.
And also
once you have the topology, maybe you will get a better idea of how to do the mapping.
Okay, but the basic,
actually, in point to point, it might not be important.
No, yes, but
sorry, go ahead.
So just as a minimum, you are saying that you are sending the reachability, which okay, for when you have several points is useful. And on top of that, any other additional information that you are sending, or you are just sending, okay, here I am aligned, and here you can connect whatever you like.
So I can get to the TAPI model. The current TAPI model on the SIP, we are only exposing available spectrum right now on the SIPs, right? And the model, we have not added any more attributes on the SIPs. But on these links and on these node edge points, the packages, especially if we are actually, as of today, we are discussing even the amplifier characteristics and so on. If you expose the topology, you can actually see all the information if the vendor supports it, of course. Like what are the amplifier characteristics, and what are the multiplexer OMS does not have much, but it's mostly the OTS, and also the power monitors, power levels, and so on. You can actually view it. So that's the extra information. But the SIPs is just only the available spectrum.
Okay, but available spectrum is, I guess, is not not too much useful, right? Because that represents
Right.
the line of the transponder to the input of the ROADM. So, well, it is right.
Right. So, yeah, if others don't mind, or maybe Oscar, maybe just immediately after this, we have time, I can show the model, the attributes, or maybe I can show the attributes in 1 second, but not too much discussion.
No, just to
Or
understand
okay, yeah.
the basic,
I'll just
the
1
basic use
second show
case.
the attributes so that, but we don't want to get through too much into the thread, so we should not lose the thread.
Yeah, I guess
So
just because
in
that
the
I
service
think is
spec,
the basic of the use case 1.5 is the base.
Right, yeah. So if you see the SIPs here, all we have is supportable spectrum, available spectrum, occupied spectrum, right? That's all you have on the media channels. And on the OTSI side, which is the line port, you have this supportable central frequency and application identified and the modulation technique, right? So just the SIPs is useful just for initial, if you're just doing channel mapping, right? But it doesn't expose anything more. Now, if you go into like the resource model, we are adding more and more stuff into it, like various properties, like the power properties and like the amplifier properties and so on. So that if you retrieve the topology, you can get more detailed information. We have not gone down to physical impairments yet, those attributes, but we are actually we're also discussing exposing eye diagrams and so on.
Okay, so that means that when you set up a media channel within the OLS, that information will be exposed through that service interface point. You will have it available there.
Yeah. Not through service interface point, but through topology. That's all I'm saying. Service interface point will still be abstraction of only spectrum, but once we expose the topology, if you don't do single node but show all of this, that's when you get more details. Right now, but we can discuss further. We can discuss how much we want to put on service interface point, transfers how much information we can transfer to service interface point. And
this is Arturo. I have a doubt regarding the representation that you are making of this interface, this NNI interfaces. I saw 2 knowledge points and 1 media channel connection endpoint in between. What are representing, which is the layers that are representing these 2 knowledge points, basically? So in the side of the transponder and also below in the ROADM node, you have this second knowledge point in the top. So I don't get very much which is the purpose of that, or which is the layer that is representing that one.
Which these ones, right? You're talking about this node edge points here, the layer.
Yeah, in the other border there, yes, that one and the other one,
right?
Yes.
Yeah, I'll if you can wait, like we'll just. I didn't put it because I didn't want to add too much label, but I have slides later on which expands that. But since you asked, right? So the node edge points, what we had a lot of discussion, and it's just called photonic layer, right? So I can do one thing, show more information. Just give me 1 second. So maybe I can update the slide deck with some information on what is on there on all of this. So if you can see my Papyrus screen, the node edge point, right, ignoring a lot of other things, it has a layer protocol name, which is photonic. And then it has supported SEP layer protocol qualifier, right, which is 1 ... Okay, now this is all photonic node edge points. All these node edge points are layer is photonic. But now, in this case, this node edge point will only support OTS SEPs. And this node edge point will support OMS SEPs. So you can call it OTS node edge point and you can call it OMS node edge point. We just called it photonic and just the link. So that's something that we have some discussion, whether we should label this as OTS or we should just label it as photonic. It doesn't, it's not, but I'll update that with labels so it's clear.
No, it's perfectly
now on this
fine.
side, yeah. On this side, this one particular, we have some discussion on what to label it. Temporarily, we called it OMS, but we say OMS is not right. So we might call it OPS, optical physical section. right? So that's why I just avoided label in this discussion, but kept it simple, high level at this point. But I have some slides which expand on it a little bit more. But
Okay.
if you can go ahead and
Exactly.
just ignore the layers for a
Go
second.
ahead and we pass this point because I still have some points on my personal presentation that I have to make.
Right. Yeah. Others will will not be sufficient. This call. Yeah. So now the thing is, now the first thing, the assumption is here now the client will send the ONOS a photonic connectivity service request between the transponder line ports. Now it's important to know that this is not a very valid scenario because all the client really knows is what the transponder supports. It doesn't know what is really available down because this topology is not exposed. But this is just a use case, right? A scenario, whether it's valid or not, useful or not. So, and then the ONOS does the path computation because it is aware of the OLS topology, right? And in this photonic connectivity service, this photonic CSEP identifies the line side SIP and includes the OTSI parameters, right, to tune the transponder. But then the ONOS either rejects the request or it makes a request to the OLS controller to provision the basically media channel. And here, like the photonic SEP identifies the network media channel and the SMC spectrum on this. Now, once that is all set up, I'm not sure what happens internally, but because I want to first go through the scenarios and then we'll go into the resource side. Then the DSR connectivity request is sent from the top, right? So this is a two connectivity requests coming from the top example. Right, the DSR connectivity service request identifies the transponder client port and the ODU client type that you want to provision, right, and capacity. So, and in case of DSR, it's simple. The capacity is fixed; it's not variable, so we don't have much to do there. Now, the second use case, the second scenario rather, is where your OLS topology is exposed on the ONOS NBI. So here, this whole figure, like the whole figure is actually what is on the ONOS NBI. The OLS or SBI context is not shown because it's same as the previous slide. There is no change in that. But now on this side, the SIPs are all same. But the key thing is the ONOS will create in this northbound context, it creates an interdomain link, right, by mapping the OLS SIP to its photonic SIP. So in the previous one, since it didn't expose the OLS topology, it didn't have to do this, right? It just left it like this. But in this case, this is a more, I would say, more reasonable use case because it provides a more complete topology to the northbound so that when the connectivity, so in this case, the domain topology is not just transponder, but also OLS, whether it's single node or multiple node, that's irrelevant. But the key point is when now the client makes the request, it has a better chance of, or better chance of succeeding because at least it knows the wavelength assignments. It doesn't, of course, we are not, if this topology has reach, I mean, it cannot really compute reach and so on, depending on what is really exposed on this. But if assuming all the information was exposed, it could have done a proper path computation and done a more valid request, right? But rest of the things don't change. And then after that, it will send the DSR connectivity request separately between the client ports. Now, yesterday a question was asked, can we use a single user connectivity request? The answer is yes, but we typically have not done that before, right? What you can do is in TAPI, we allow to have CSEPs for a connectivity service request, which are of different layer protocol than this connectivity. So you can specify in a single request, not just the client ports, but also the line ports, right? As CSEP, saying, okay, this is what I want you to configure on this. This is what I want you to configure on this. So it is possible to do it as a single request. We just typically, we didn't expose or we didn't articulate our use cases like this. The only place we have used like this in TAPI is an Ethernet case where you have a C tag and S tags. So originally we defined this for that kind of scenarios, but you can definitely do this. It's really how ONOS can handle or not handle the request. But of course, it has to understand the difference between this CSEP and this CSEP. And when we as a human present it on a GUI like this, we can see this nice sequence. But in the code, you have to understand what the semantics of the CSEPs are. but it's definitely doable.
Mm-hmm.
But this was a question that we had yesterday, whether you can or cannot. And we did add like layer protocol name and things like that to the CSEPs long back for this kind of scenario.
What about
So the service
constraints
is
about
still
the media?
DSR service, but yes, yeah.
Yeah, you can include the CSEPs of the OTSI layer, but can you specify constraints like which is the lambda that you want to use?
Yes. I'm assuming this is, so I'm assuming it's an photonic CSEP. So that means you augmented this, you're using the, let me quickly show you, you're using this argument here. Yeah. So that you are actually specifying whatever you're actually doing, the media channels and all the attributes, the transmit power, the modulation technique, and so on. So the assumption is yes.
Okay.
And the DSR CSEP is identifying this, the client-side port parameters. Right. Now, I'll just quickly go through the resource view and then hand it over to Andrea. So this is a simplified resource view for this particular use case. So the ONOS receives the photonic connectivity request. It in turn sends an connectivity request to the OLS controller. Now, based on that request, the OLS controller will create the network media channel based on the attributes which are specified in the CSEPs, right? So it will provision this if it's possible. If it's not possible, it will reject the request. And this will result in a photonic link, like in this domain. So now you know that you can connect this node to this node because there's a link between these two nodes, and you can create a OTSI connection over this link, right? And right now in this use case, there is one-to-one between this OTSI and NMC because we said that there is one lambda per wide media channel, but there are other cases in TAPI where we can actually do some multiplexing. And then now this is all that happens in response to the photonic connectivity request, because all we have done is provision the photonic side. Then you have whenever you receive the DSR connectivity service request, you provision the ODU connection and the mapping to the client rate, right? Because the DSR connection is basically telling you what is the client rate that you are using for this service. The reason why this is done on DSR connectivity request, I have not drawn the use case, but I'll draw a second scenario where you have mux ponders, right? So then when you have multiple ports, all of these ports are muxed over the same OTSI. So then there is different ODUs. So if it's like a 100 gig transponder, then you can have 10 gig ports, and this is ODU2 connections, right? So those scenarios are not described in this use case, but that's the reason, like when you have mux ponders and so on, you want to provision the ODU or whenever you receive the DSR connectivity request, because that's when you turn up the ports, the client ports, right? So that's all I have for today. Before I go, so this is a complete model, resource model. In the previous model, I just showed that the OLS only provisions network media channel and nothing else because there's one-to-one. But like this is a discussion we had in TAPI and Facebook tip guys and so on. When you receive the photonic connectivity service request, they provision something called what is called service media channel. The service media channel is a wide media channel, so it can contain multiple network media channels. So one SMC can have multiple NMCs, and your single OTSI can be supported by your ODU or OTU connection is supported by multiple wavelengths, right? So this is a full TAPI model, which I didn't show because for the first use case, all these are one-to-one. So you really don't need to show these assembly steps and assembly connections, and you don't need this hierarchy. But in the case that where you have one media channel, which is sort of carried over a wider media channel across the network, then you need this service media channel constructs. And in the case where your OTU is supported by multiple lambdas, you need this OTSI media channel assembly connection, which groups these. So this is more a full model, but the whole idea is that you only bring in the complexity when you need it. If you don't need it, you use the simplified view of the model because everything is one-to-one, so don't need to model the additional connectivity. because they are all one-to-one.
Yeah, hi, I wanted to ask this question. You had made an assumption previously that the connectivity was already established. So are you assuming that between the two end ROADMs here shown in this diagram, the far left and far right, that those end-to-end, there's one or more end-to-end wavelengths that have already been determined as feasible? That connectivity has been established. That's what you meant by that. Is that right?
Okay.
It was an earlier assumption that you stated, right?
Yeah. Right. So there are two cases actually. I made the assumption first that at least at the OMS level, your connectivity is set up. That is, you don't have to worry about arranging or configuring your amplifiers and multiplexers, right? Now, beyond that, there are two cases which I mentioned here, which is optionally you could either specify the SMC spectrum or this spectrum can be set up, right, through pre-configured filters. So then all you are really doing is turning up and turning down the transponders. So both are possible. I've not explicitly called it out in this case. Does that answer the question? So I could have made another use case, sub use case, where I show this SMC setup beforehand. Right. This is this is a Facebook terminology. They call it service media channel. So the service media channel is where you actually set up this wide spectrum through the whole ROADM network. And then after that, we are just simply turning and turning of transponders and doing power control. So,
right. So in other words, you're pre-configuring the end-to-end connectivity of the wavelengths, and then in this case, you're sub-selecting the transponders are choosing as long as they are they can transmit, they can communicate in that range of wavelengths that have been pre-established.
Yeah, I'm allowing for both because I don't know what the group will decide. I just present it as a use case or how you can do in TAPI. And now, as a group here, we have to decide what we want to do. So that's where I'm not saying what we should or should not do. The short answer is it's really up to the OLS.
Yeah, the OLS in principle can compute end-to-end connectivity based upon the request. It just has to know what is the requested wavelength and whether that wavelength is available end-to-end, impairments included. It would do that calculation, right?
Right. Yeah. If you want to avoid doing that, yes, you can set up. You can pre-configure the SMC and advertise it when we advertise the topology. So then, basically, once you have this, what is called SMC in Facebook terminology, that's basically where all these impairments are considered and the grids are set up, filters. And then after that, it's just a matter of turning on these NMCs, the transponder connections, and doing the power monitors and tuning the powers. Right,
which is fine, but it reduces. Sorry, so it just reduces the dynamic nature of the network, right? So you're pre-configuring a lot, and launching it.
Actually, I can make that as a sub case. I didn't make a slide specially, but probably I should do that as one of the variant of this use case. I'll do that actually. I'll update the deck to show that variant too, where you have this setup, and then you're only doing the NMC. So as far as TAPI is concerned, as an request, let me just use any one of these slides. So when you make this photonic connectivity, you have to specify your transponder central frequency, but everything else is optional. So your NMC is required, but your SMC is optional. So your wide media channels could be pre-configured. It's not a required.
Okay.
And I'm using the word wide media channel, but in this case, your SMC is in this use case is one NMC. So it's actually you're actually setting up this channel throughout.
Okay.
Thanks,
Karthik, for the presentation. It was very enlightening, and I think it went in depth and properly exposed the things that we could do. Let me take back my screen. And okay, so having said that, I will send out an email with Karthik presentations and a request for you to vote if you would like to do it with 2 requests or 1 request. I have a personal opinion, which is I would like to do it in 1 request because that makes things, in my opinion, simpler for the overlay, meaning the OSS, BSS, whoever controls this whole system. But I'm open to do it into actually inside ONOS. It's simpler if we do it with two. So I'll send out an email and we can discuss that. Okay, having said that, we then need to map the request that we just made, the one and the two request, to existing ONOS APIs. So in the first phase one, we've done it through the configurable transceiver class and setting up the cross connection between the two ports. At the moment, since we need also to control the OLS and the RODMs, we would need to map the line side to line side connection request to an intent which is the optical connectivity intent. And Ramon and Alessio and the people from the Metro Hall project with Tim and Telefonica and other vendors already did this for the RODM use case. So we know it's working. We're just going to use an optical intent with the two ports. But we will need to map the TAPI stuff, TAPI objects to ONOS ports. So to do that, basically we will have a set pair that identifies a ODU CLT if the device is a transponder, and the request that comes in is a layer 2, or they are the two most endpoints of the single request. We're going to have a couple of pairs that identify OCH port if the request is a layer 0 request, or the two internal points that Karthik was shown before. I'm sorry, my terminology is not the best in this case, but it's okay. One point that is very important and that we made sure that is already done is that when exposing the topology on the northbound, the request will come in the form of UUIDs identifying the port in the TAPI request. So what it will happen is that ONOS will do the mapping to the ONOS port through this UUID. The mapping is done through an already kept mapping internally that is done when the port is discovered. So during the device discovery, ONOS discovers the port and assigns it a TAPI UUID. That TAPI UUID is the one that will be exposed to the northbound, and it will be used when a request comes from the northbound to translate it to an actual ONOS port. So that is done. But one thing that we will need to do is that we will need to augment the ports in order to use the intent that we discussed here. We will need to augment the ports in the driver. What I mean by that, that currently at the moment, the ODTN device description discovery implementation only assigns the type to the port. Instead, what we need to do is to augment them with optical port information. And that optical port information, I can show you an example. Can you guys still hear me?
Yes.
Okay. So I can show you an example but that Ramon sent today. Basically, in the discovery of the device, we will need to augment the ports, and I've added some comments here, but don't worry about that, with basically the channel, the signal type, the audio signal type, and other elements. That can be done through the use of the OCH port helper. As you see, this is a small amount of code that needs to be done in the drivers for the augmentation of the ports. That is needed because the intent requires those information to properly set up the channel. This is how internally ONOS keeps that information. So at that point, when the intent gets issued, this piece here, it will go down to what we call a flow rule programmable, which will generate an XML payload that will be sent down to the device through the netcom session. At the moment, we are currently also in the process of sketching out and building the DCS 2.0, which will be needed. But in order not to hinder our progress on the connectivity side, we will create a common interface. We will create a common interface here through which the XML payload will be sent to, that initially will just act as a pass-through. And then in the future, we will add DCS 2.0 when that is done. So one important point that we were discussing yesterday is that this flow rule programmable that does the translation from the concept of a flow rule, which is a match action, to any given XML payload that needs to be sent down to the device, needs to keep some state, because ONOS expects these rules to be returned to him as they were sent down. This is very hard to do in the case of non-OpenFlow devices. So a solution that we are already using in the P4, and I would suggest here to do, is to use the cross-connect cache. This was partially used already in some drivers, and I think Ramon and Alessio have an experience with this. It would probably need some augmentation, because currently at the moment is a single instance of the ONOS. Instead, it needs to be shared with a shared map. We can rename this. At the moment, this is storing a mapping between a hash and a flow ID and a priority. In my opinion, this is good enough, because you would compute the hash given any parameter that you can send down to the device and can retrieve. So you will compute this hash, and you will inject this hash and the flow ID that ONOS gave you in the cache. Then, when
So Andrea, you're recommending computing the hash on that XML file, right?
Yes, that XML file or any number of parameters that you send down.
Okay.
How you compute the hash, in my opinion, is really up to the driver, and we will come up with a unique way based on the OpenConfig XML payload that will need to be sent down, or the TAPI payload that will need to be sent down. We will come up with that as an ODTN general way of computing the hash, but that integer can be whatever you compute, and you're able to recompute in a given way, and that doesn't change, meaning that at some point you will need to retrieve that flow ID in order to get the flow rule and return it to ONOS so it can say, okay, it was installed. If you're not able to... Please go ahead.
I'm sorry, I was just going to say that my only concern was that the XML file alone there's a possibility it could be a duplicate. But if you were to put a timestamp on it or something, that would,
Yes, exactly. I can actually do this.
Yeah.
Let me put here to
okay.
Add some hashing suggestion, something like that. I'll do that. And the idea is that at this point, you saved the state of something that you saved a mapping between what you know is on the device and what ONOS needs to do. So whenever the ONOS requests again a flow rule, you will compute the hash on the existing parameters inside the XML that was given to you by the device, retrieve the flow ID, and after you've retrieved the flow ID, you retrieve the flow rule from the store and push it back to ONOS itself. I know this is currently a workaround, but I actually do not see any downside of this. So, Ramon, any thoughts?
I can comment a bit on something similar that we've been doing with Alessio, but this is for OpenRhythm. I know it's not still the phase 2.0, but let me connect on this. As you said, by design, ONOS drivers are stateless, so they assume to be a stateless code from the core of ONOS. This is something that Mark said it's by design. And in the specific case of flow rules, in very simple terms, what we are getting once we are running the system is basically flow rules that tell you the ONOS incoming port, the optical channel signal, ONOS outgoing port, and optical channel signal. If you need to then map this to OpenRhythm XML, well, OpenRhythm requires managing NMC, MC interfaces with long names, lots of attributes that you have no means to store easily. So what we need to support OpenRhythm is we have a synchronized map per device. So you have your device netconf, blah, 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 and then a set of connections. And that connection is basically a data structure that maps this very flow rule specific ONOS input port optical channel to all the information that you actually need to support the OpenRhythm. And this is, as Andrea perfectly said, this is a bit like a hack. We will have some code soon. It's still being worked on. And we still have questions because we need to know, for example, what hypothesis regarding multi-threading ONOS is doing. It is clear that for a given device, at least there is one thread, but for multiple devices, which can be in parallel, multiple devices may access that cross-connect cache, or call it as you wish. So we need to synchronize it as well. So in very simple terms, right now,
yes.
Yeah.
I think
Go ahead.
that we need a blend of the two approaches. I agree that it might not be enough to store the hash to flow ID mapping. We can discuss that, and I would like to see your implementation, or at least your idea. But in turn, what I am proposing here is basically a distributed store, an ONOS distributed store, which is not going to be in the driver per se, because is not going to be a driver component. It will be sitting in the driver tree, but it will be a separate distributed component that will allow us to save whatever state is needed for the mapping. So what I can do is show an example of what I mean here, and create a slide and then share it with everybody. And I would like to see the code that you have written in order to see if I can align myself best.
I just send it a very short, well, you will see that we can discuss it later on, very short email of something that we did precisely like this. It's, again, in very simple terms, the driver itself has a static variable towards a single instance, which is a synchronized mapping devices to whatever connection cache you need.
Okay, yes. This, I think we already do this in P4. We can reuse some of the concept in there. But point being, there is a solution for that mapping, and it's fairly trivial to implement, and we can borrow and steal.
We should align on this. A second question was, what are the assumptions regarding multi-threading? Is it possible that multiple threads may access a single device
at the same time?
I guess.
Well, it depends by the implementation of the map itself, and what you store into it will issue the.
Not just the map. Let me explain. You know that flow programmable has several methods. It can be retrieve flows, get flows, or add flows, or whatever, or delete flows. Is it possible that thread A is retrieving the flows and thread B is adding flows? I know that this is yes for different devices, but for the same device,
It can be.
Okay.
There is no assumption on access to the device because at least in the way we design the APIs, we had plenty of agents for devices that were assuring us consistency. I know that in some other implementation that we have done that deal with access to the device that needs to be consistent, we've synchronized the structure of the information, meaning the map that was storing the information, in order to basically synchronize the calls. So I think that the cache we are discussing here will be synchronized. Okay, so I know we're running out of time. I will defer probably this discussion to a later time. We already did some of this, and probably next week at this point. What I would suggest everybody to do is to give a pass at this document. This is the proposal. The code is almost, I know that parts of the code are coming already, and I already have a list of to-do that we need here. I will send this out in the email with with the vote for that we were discussing before for 2 requests or 1 request. And I would like next week to be mainly focused on questions that people would have on this presentation. If none arise, I would call this good, and we would go forward with the implementation itself. Ramon, we might want to schedule a one-to-one between you and me, specifically on the implementation of the cache. But let me defer that to an email discussion.
Yeah, of course. No problem.
Okay. Let me go to the agenda, see what's there. Okay, so if anybody wants to learn more about the implementation details that we discussed yesterday, there is the link over there with the implementation discussion and the recording of yesterday's meeting. Current state of the driver, I merged the Nokia driver a week and a half ago. Currently, the code is working. We put in a patch for fixing DCS issues that we were having. I need to merge it, but it's okay. It's there at least. I know that the Metro Hall OpenConfig drivers are also coming thanks to Ramon's patch. I've seen that today. I've posted some comments. Hiroki, any update on Infinera drivers?
ON.Lab members are completed their testing, and now they are ready to upload for reviews. So yeah, they can upload the patch in a couple of days.
Perfect. Okay. As always, there is the configuration document that describes the DCS 2.0 ideas that we wanted to do. Please take a look. Any more points that anybody wants to discuss? Great. If not, I will send out an email with the recap of Karthik's discussion and the vote for that, and the link to the document asking everybody to review. One important point that I want to review is since all the open questions that I put in there, and if you guys could read at least these open questions, especially around this, and my proposed solutions, which is answer. Please give your thoughts. And I also put the OLS topology discussion over here. So please take a look and provide some comments. And we will address all the comments hopefully next week. I'm going to be on PTO, but I'll try to ask somebody to pick up the meeting and lead it. If not, I will reschedule it to the week after. So thanks, everybody.
Thanks, Andrea.
Bye-bye.
Bye-bye.
I will send out an email.
Bye-bye.
Goodbye.